Okay, good afternoon. I have the privilege to introduce you, Dr. David Schoenwald. Dr. Schoenwald got his PhD degree at the University of Ohio and has an extensive experience on projects, electrical projects and research projects at the National Lab. Today he holds a position at the Sandia National Lab, and today he will talk about oscillations in the West Coast, in the National Grid West Coast, and the focus will be the HVDC line using real measurement. And thank you so much for joining us today, Dr. Schoenwald.
Oh, let's see. I think I'm okay.
Okay.
Well, thank you very much, Hector. Really appreciate the introduction and the invitation to come out here. Can everybody hear me okay? Okay, great. Thanks to Lisa for setting up the visit and the tours today. Really appreciate that. And also with Elu, Dr. Elu Liu, for talking with her later today. And I want to introduce my colleague and my boss, department manager of the Electric Power Systems Research Department at Sandia, and that would be Dr. Ray Byrne in the back. Say hi, Ray. Ray is a fellow of the IEEE, and he's department manager there, recently became department manager, and he also has been involved on this project as well. And most of what I'm going to talk about today is in the category of small signal stability. These are oscillations on the power grid, mostly large, wide area power grid oscillations. And the project began about 6 years ago, almost 7 years ago now. And the project has since ended, but a lot of the work that we're doing today has evolved from work that I'm presenting in this seminar. So I'm going to talk a little bit about the background of the project and what we did in terms of control. And we did actual testing on the grid. So we actually got the chance to demonstrate our controller and get a chance to take a look at how it does versus the no control case. And we used PMUs, phasor measurement units, or synchrophasors for real-time feedback data for our control system. And whenever you throw in a communication network into a closed-loop system on feedback control, that introduces delay, plus a potential for drop data, corrupted data, and I'll talk a little bit about that. And then I'll talk a little bit about, since most of this is focused on the PDCI, the Pacific DC intertie, I'll also talk a little bit about the use of modulating wind turbine power as well as energy storage at the end of the talk. So I want to give some acknowledgement to different people, and in particular to the programs that funded this work. The DOE Office of Electricity Transmission Reliability Program. Many of you know Phil Overholt, who his program also has supported the CURENT Center now for a number of years. And also co-funding our project was the Energy Storage Program, a sister program to the Transmission Reliability Program in the Office of Electricity, and that's headed up by Dr. Emre Juk. And then finally, our customer and collaborator in this case is the Bonneville Power Administration, which is a transmission authority, a little like TVA, except they don't own generation. They do transmission, and they have an Office of Technology Innovation, and this was a project within that office, and it was funded under that office, in addition to the co-funding from Phil and Emre's offices. And at BPA, our primary technical point of contact, and if you're familiar with power grid oscillations, really the dean or the godfather of the West Coast for power grid oscillations is Dr. Dmitry Kostarev, and he is really the one that was the vision behind this possibly implementing this particular control system. Gordon Matthews was our project manager, and then there's a host of folks at BPA that we worked with at varying stages of the project. And at Sandia, in addition to myself, you see, in addition to Ray, several other individuals that have been there now for a few years. And at Montana Tech, Professor Dan Trudnowski was a co-PI on this project, And he's another one who has tremendous experience in oscillations on the Western grid. And so between Dan and Dimitri, we really had two of the preeminent gurus for oscillations in the Western grid on this particular project. So let me just give you a brief, quick overview of what we did before diving into any details. I'm not sure what everyone's familiarity is with power grid oscillations, but power grid oscillations that we're looking at are the inter-area oscillations, which cover, in the case of the Western power grid, hundreds, even close to 1,000 miles. And whenever you have long transmission corridors that you're stuffing a lot of power into over hundreds of miles, these oscillations become a natural part of the grid. And you can have multiple oscillations on a grid if you have multiple transmission corridors, as is the case in the Western grid. When these are not well damped, and in particular, if you have high load, such as in the summer, air conditioning load, and you have things happening on the grid like a line fault, line going down or a generator tripping off, then these oscillations tend to become poorly damped, and in fact, they can even go stable, and I'll show unstable, and I'll show an example of that. So to keep that from happening, what they do in the West Coast is they constrain the power flows below the ratings, the thermal ratings of the transmission lines. That means they essentially leave revenue on the table. They aren't able to fully utilize the capital investment that has been made in the transmission infrastructure. And so that's not very efficient, not very economical. So what we did is we constructed a feedback signal using real-time phasor measurement unit data. And phasor measurement unit, PMUs, which you guys have here in the building, are devices that measure frequency, current, voltage. They give you a power flow. They give you this data over a communication network and they can stream it at 60 hertz. Some go faster than that. And using this as a means of closed-loop control, feedback control, has not been done before, at least not in North America. And there may be a couple examples, one in Sweden or in the Norwegian area, and then one in China. Otherwise, it's not been done in the world for real-time PMU feedback control. And so that's really the innovation of this project. The biggest one is that we're actually using these devices in real time to be able to construct the closed-loop control signal that will damp these oscillations. And for the actuator, we use the Pacific DC intertie, which has been there for almost 50 years now. And we modulate the power flow. So we add and subtract to it delta up to plus or minus 125 megawatts. And then finally, if you're going to do this on the power grid and you're actually going to get permission to test this, they're going to give you one commandment that you absolutely do not want to violate, and that's do no harm to the grid. That is the absolute inviolable commandment that Dimitri gave us and said, above all, you've got to have a means of making sure your controller doesn't make things worse. And that's not just the oscillations that we're trying to control, but other oscillations that we don't have control over. We don't want to make those worse. So we implemented a supervisory system, which I'll talk a little bit about in the talk, that ensures that that doesn't happen. So why do all this? What's this going to be? How is this going to benefit the grid? Well, it will improve reliability. And in a stress condition, having this controller online, functional, operational, gives you an additional contingency to handle high load days and in addition to when you may have other events that stress the grid. Now this one avoided costs from a system-wide blackout. Well, this actually happened in 1996, and the costs associated with it, all the costs, economic, lawsuits, everything, ran into the billions. And BPA in particular, just alone was close to $2 billion. That's a lot of money to lay out because of a blackout. And in response, constraining the power flows is an economic hit that they have to deal with on a regular basis. There's also the transmission infrastructure deferral, or possibly a reduction in new transmission capacity that's necessary because you can utilize the power transmission corridors that you already have more efficiently. And so this can help you meet increasing demand by having these higher power flows on these really congested transmission corridors. So here's the event that really was the genesis of the project way back in 1996. And this is about a 10-minute time series of power flow between the Oregon-California border, and basically going from north to south through the AC corridor there. And it was a day in August of 1996 when there was a lot of, there was a heat wave in Southern California, so there was a lot of air conditioning load, and so a lot of power was being transferred from the Pacific Northwest, where you have lots of cheap hydropower, and pushing that through the AC corridor down to Southern California, Central California, Bay Area. And that right there put the grid in a case where the damping, in this case 7% damping, is not real good, but at the time they felt that that was okay. And simultaneous with that, in the Pacific Northwest, there's a storm going through. And it knocked out one of the major transmission lines, and that caused, as you can see, a momentary instability, brief, for 15, 20 seconds or so. And the damping got even worse, and then it was able to recover from that. The grid can handle at least one contingency. And so you can see that it's struggling. Damping is not very good at all. And in fact, you're at a point where if one more thing goes wrong, then you're really looking at the possibility of a system breakup. Well, that one more thing did go wrong. And that was pretty much the same storm moving through. It took out another line. And that line, once it was taken out, the generators now suddenly are separated from their load when you have this system breakup. And so what happens there, generators have protection, they trip off. And so at this point, you've got a completely unstable grid. And this, right here, obviously that's the classic, it blew up. And it resulted in what they call a system breakup, where the north and the south of the western grid were disconnected. And so that led to widespread outages. I think it was around 10 million people lost power, and not for just a few minutes, but hours, even overnight on into days. And there was some damage to some of the generators. There were lawsuits. People didn't have the backup generation, so you have people with medical issues, and there were just all kinds of fallout from that lasted months, even a couple of years. And so for BPA and the other West Coast utilities, it became sort of an alarm that said, okay, we can't let this happen again. And the response to it is to constrain the power flow well below the limits that they were operating under at the time. And if you're BPA and you're selling power through your transmission lines to Southern California, that's a big revenue hit on days like that. So the map on the right shows the western interconnection in yellow, and it shows these inter-area modes. The one in blue is what's called the north-south mode, and it is the one that was identified as the primary culprit in the power system breakup that you just saw. And that, when I say culprit, you could say, well, it was the storm going through, taking out two lines simultaneous with a very hot day in Southern California. But it should have been able to handle that if it had an additional damping capability, the ability to actually add damping, and it didn't. So this north-south mode became the subject of a lot of study. And there are other modes. The red one is the Montana Pacific Northwest mode, and the orange one is the east-west mode between Colorado and Southern California. And these oscillation mode frequencies can vary depending on the load in the grid, and they vary over time as the grid evolves, more generation, new lines constructed. But they're typically under 1 hertz. And the case of the north-south mode, it's about 0.4 hertz. And these two modes are a little higher. They're maybe 0.6, 0.7 hertz. And the physical phenomenon going on is where you have generators in one part of the grid, in this case, Pacific Northwest, and another part of the grid, Southwest, that are oscillating against each other. That is, the rotor speeds are actually speeding up in one part while the other slows down just a little bit, and then it flips. And it does so, the frequency at which it flips is the modal frequency of the oscillation. And as I said, that's about a 2.5 second period, 0.4 hertz. And that really was what caused the fact that that was so poorly damped was the primary culprit in that outage. And so, as I said, it became this subject of a lot of study. And the idea of these inter-area modes is not a new thing. That's been known for many years. And it was thought that they're pretty stable. The natural damping is sufficient. But they were at least worried in the 1970s that they decided that, when I say they, I mean BPA, Bonneville Power Administration, that they at least wanted to do some testing on modulating power on the PDCI. And the PDCI is a high voltage DC line, the Pacific DC intertie, that connects northern Oregon, right on the Columbia River, about an 1.5-hour drive east of Portland, and Los Angeles, San Fernando Valley. It's 850 miles long, and it's a straight shot. There's no connection in between. So it's just delivering power, and in this case, the capacity of it is 3,225 megawatts. That's 3.2 gigawatts of power that it can transfer over this DC line. And it was built, as I said, in 1970. The power electronics at both ends have been upgraded multiple times since then, most recently about 2 years ago at BPA, not necessarily at the same time. So Silmar had more recent upgrade, and now they'll be the next one to get another upgrade to make sure that the power electronics stay up to date. And what BPA did is they decided they would control the modulate the power, and they would use local measurements to tell them what is going on with the grid to see if they could improve the damping a little bit. And they felt pretty good about the results until they started looking at other modes or other stations in their region, and in particular, they actually started looking at north of the border. And there was a concern because the oscillation between the Pacific Northwest and Canada, the Canada mode, which is the green one, the BC-US mode, that one was destabilized. Now, nothing happened. There wasn't a major outage, but it was enough to scare them to say, okay, we're not going to do this again. So fast forward to about 2007. The game changer is the phasor measurement units, which is the ability to know what's happening on the grid simultaneously, or very close to that, at many locations throughout the grid. And it's a way, it had been developed at Virginia Tech, and it had been promoted heavily, has been promoted heavily by DOE through Phil Overholt's office. You guys also have had a huge role in that, the FNet in particular. And then it has also been adopted by BPA. BPA in turn has been teaching other utilities how to implement PMUs, how to set up a communication network, what the data can be used for. And so now the thinking was, well, what about using these for feedback control? They weren't developed for that. They were developed to do forensic analysis, looking at monitoring, various kinds of surveillance on the grid, but not to do actual real-time control. Maybe some might inform an operator decision, but to actually close the loop on it at a 60 hertz control update rate was not part of the original purpose of the PMU. However, BPA, Montana Tech, thought about, well, why not? Could you do it? And so that's where this project was born. And as I mentioned, a lot of the deployments of PMUs throughout the West and in this part of the country as well. And so the project began in 2013, and we first did a lot of work on trying to understand the grid. So a lot of eigensystem analysis, simulation studies, a lot of prony analysis to understand these modes, and a lot of study of PMU data quality. What are the latencies associated with them? How often do they just drop off? Do they produce or transmit unreliable data, corrupted data, missing timestamps? We needed to understand that data quality a great deal before we could even think about closing the loop on it and actually testing it on the grid. We, simultaneous with that, did a lot of controller design and a lot of studies using different models and different simulation packages. We used MATLAB a lot. We also used the what's called PSLF, which is a GE product. Some of you are familiar with it. I think you guys probably use something called PSSE a little bit more. So it's kind of a sister package to PSSE. The same guy invented both, John Undro, by the way. And John Undro was initially a consultant on this project. And he's really the third guy. I mentioned Dmitry and Dan Chudnowski. I also need to mention John Undro as well. And he developed PSLF. He developed PSSE. He's a professor, like a part-time professor at Arizona State, and worked at GE for quite a while. So that was what we did a lot of our simulation work in. And so finally, Dmitry said, okay, it's time to roll. Let's roll it out. We had hardware that we had developed, and we had been running it sort of in like a emulated setup, but we hadn't actually connected to the grid. And so starting in 2016, we got permission to do one day of tests. And we did. We got very good results. And about, let's see, 7 months later, we got permission to do another. After that, we got permission to do yet another series of tests. Each time we want to confirm what the previous results were, that it's still working, but also we want to, each test expands what it is that we're testing the controller to do. And I'll talk a little more about that later. So the project ended about a year ago. We're wrapping up the documentation, but Phil is still funding us, and our work has really evolved now towards transient stability. So what I've talked to you about is small signal stability, these oscillations. Transient on other sources of actuation. So here's an overall graphic of what the controller looks like, and just a block diagram. So the damping controller itself has three components to it. There's the real-time control, and the real-time is what does the calculation of the feedback signal. It takes in the PMU data, computes the feedback control signal, and sends that to the PDCI to modulate the power on the PDCI. Another part of it is an asynchronous part, which is slower than real time, and that includes the supervisor that is supposed to prevent no harm, and it also includes the GUI, the operator interface, that tells you what's going on, and there are some settings as to what PMU data you're going to use, and so that's where the operators can interact with it. There's also a faster than real-time part of the damping controller. Anytime you're going to implement a critical system, something that's going to be deployed in real time that you don't want it to fail, or if it does, you don't want it to do something damaging, you really need to monitor the local, the device itself, and make sure that the hardware is functioning correctly. And so we have what's called a watchdog circuit that keeps probing every part of the control system, and including the connection to the PDCI, that says it's alive, I'm doing fine, and if any of those drop off, then the controller needs to be gently disarmed so that there's no spurious signals injected into the grid. And it also includes, of course, you'll see a picture of it in a moment, the red panic button. That has to be there too. So that's a block diagram of the controller. So how does the controller then interface with the rest of the grid? And that is what this diagram shows. So the dashed lines are everything that you just saw in the damping controller. And outside the dashed lines is the rest of the world. So the PDCI itself, the northern part of the PDCI is in a place called Celilo Converter Station. It's in a city called the Dalles, Oregon. It's right on the Columbia River and very scenic spot near Mount Hood. The southern end, as I mentioned, is in LA. So we were at the northern end. And BPA owns and runs that Celilo Converter Station. We interface directly with the commanded power that is going onto the PDCI. And that is denoted by this P scheduled. And so our commanded power simply sums into that. And that is the net signal that is sent to the PDCI controls in Celilo and produces the DC power, the command that will convert the AC power that's coming in and convert it to DC to go down those 850 miles. And then to LA, where it gets inverted back to AC and dumped into the grid. And so this is the grid, and these are your disturbances. We have PMUs, north and south, that we use for our feedback. And these PMUs, we have more than one in each location. This is where we are getting our signals. And so these lines here represent the data network. So this really is a communication network. Our controller has two filters, well, one for each of the signals coming in. That is a low-pass filter, and it does that to clean up a lot of the noise that's there. But also, what we're trying to control is something that happens at 0.4 hertz, less than 1 hertz. So we want to make sure that we have full control authority, less than 1 hertz, and greater than 1 hertz. We don't want to do anything. We don't want to mess up the governors, the speed governors on the grid. So we have a low-pass filter that filters that higher frequency. There's a little bit more on things like the filter delay. So if you're interested, there's plenty of papers that describe the exact kind of filter that we implemented. But it's a fairly low-order filter, second order, and that was done so that we wouldn't have a lot of filter delay. However, it also means that you don't have as sharp a cutoff, and so there's a little bit that comes in over 1 hertz, but not much. We take the derivative because what we're getting is the phase angle, and what we want is the frequency. And the difference between the frequency in the north and the south is our feedback signal, delta F. And that is telling us what is the frequency difference between the two areas. And as that signal gets larger, there needs to be more damping into the system. And so we then put that through our control gain module. And we have this saturation limiter. I mentioned that we're allowed to modulate plus minus 125 megawatts. Now, I told you that the PDCI can carry up to 3,000 megawatts. It doesn't do that every day. But typically 1,500, 2,000 megawatts. So 125 megawatts is not a lot. It may represent 3, 4, or 5% of the carrying capacity of the PDCI. But it's more than enough to get significant damping. And these Pmax and minus Pmax, you may wonder, well, where'd you come up with those numbers? They're probably more, I mean, there's technical reasons, but there's probably more, I don't know, political is the right word, but operational. People get nervous when you're doing stuff on the grid, and they want to know you got limits that you can't violate no matter what. Because no matter what you tell them, oh, no, we'll never do that, they want to know that, no, we're going to make sure you can. And so it is saturated, and that is the signal that comes out of our controller. And mathematically, this is what it looks like. The K is a constant gain, and it has the units megawatts per millihertz, and it multiplies the difference in the frequency between the north and the south. These tau parameters represent the time delays in the network, and I'll talk a little bit more about that. And then these numbers, 1 through 5, are the sequence of events that's occurring in a typical control update cycle. The PMUs measure, they send the data out over the network, you get the data at the controller sends a command to the PDCI, and the PDCI injects the power. And repeat that up to 60 times a second. And the controller has a GPS, so when the data comes in, I think most of you know that PMU data has GPS timestamp, controller has timestamp, and so it's comparing the two, and based on that, it knows what the delay is. If that delay gets outside a certain bound, it doesn't use that data, because that data is old. And we have more than one PMU, as this graphic shows, and the reason we did that, actually the term came from Dimitri, he wanted diversity and redundancy. Diversity means geographical spread. That is, you've got more than one site or location in the grid where you're getting the PMU data from. So that way you make sure that if one location, there's a problem, a communication problem, and it goes out for whatever reason, or it's just under maintenance or something, you've got others you can go to. And redundancy means it's sort of a sanity check on your PMUs. If you've got two PMUs at the same location, each, say, on a different part of the complex of a substation, you want to have two of them where you compare them to each other, and they better be giving you the same information within some very small delta. If they're not, that tells you something's just not right there, because they should be agreeing. And if they're not agreeing, don't use either one of them. Go to a different location because something isn't right there. And you might not catch that if you didn't have the redundancy part of it. So every location that we're using has two PMUs, and so that gives us additional checks to make sure the control signal that we're going to inject is getting real quality data. So what we're doing now, and the number of feedback pairs, this can vary. At the moment, we have 4 in the north and 4 in the south. And so you work the combinations, and what we have is 16 potential feedback pairs. And one of them has been chosen by the operator to be the one they would prefer as their first choice. And the other 15 are computed every update cycle of the controller, just in case all these checks show that, hey, your first choice is a bad one, but the third choice looks good. So let's go with the third choice. So if the controller is evaluating all 16 and computing what the feedback control signal should look like, then every update cycle, you can very easily and quickly switch between them if you need to. And that is something that we made sure that the controller does implement. And that way, you can check, or you can make sure that you're able to go on a moment's notice, literally on a moment's notice, to switch between feedback pairs that are not giving you, one of the locations has questionable data. And we do this using bumpless transfer. And the reason for bumpless transfer, if you're familiar with it, is that it's just to make sure that you don't have a dramatic switch in the value that you're injecting into the PDCI. In other words, we don't want to put a step function into the system, which could produce some unsatisfactory results. So a little bit more on the supervisor, this do no harm part. It has 3 parts to it. The watchdog is the faster than real time, implemented in custom hardware that we designed and built at Sandia, and that gives us the local monitoring to make sure that everything is working fine. The operator can hit the emergency button and the controller will disarm. The real-time part, which reads in all the data, checks about. We've got a lot of different flags. If the data isn't good, or if there's something going on in the grid, I think we're up to 18 flags, and that may go up more. Most of which have a, I guess, like anding all of them together. If any one of them says this isn't good, you drop off. You disarm the controller. And then the controller implements the bumpless transfer, as I said, as it goes from on-off mode so that you don't put a step function in. And then finally, there's the slower than control part. And not all of this is actually implemented yet. What this is intended to do is automated probing, which is going to tell us what other modes are doing on the system to make sure that we're not doing any harm to any other, like I showed you east-west mode, Montana, northwest, BC, Canada, or Washington mode. We want to make sure that everything else is going on the grid. And the best way to do that is just to have automated probing right there at the location. Now, we don't necessarily need to do that, but that's a fail-safe way to do it, or a safer way. We also want to get a little bit more status on the PDCI. And the asynchronous controller can inform the real-time controller, actually go through the watchdog circuit to say, okay, we need to disarm because something that's happening at a slower rate is also of concern. But it also sends data to a locally stored supervisory or server that stores all the data so that you can download it and look at it later. It does not stream the data over the network. We get data from the network, but we don't push it back onto the network. So this is what it looks like, this photograph of it. This is about a 6-7 foot tall refrigerator type cabinet. And this is all the different hardware that is implemented into the controller. The real-time part is using National Instruments Compact Rio, or excuse me, PXI chassis. We did consider Compact Rio as well, and that may be a future version of it. And we have a supervisory function, so this is the server for that. And then this is the watchdog circuit, and this is a blow-up of this panel. The status indicators are for the various components on this cabinet, and there, of course, is your bright red. BPA made fun of us for that. They said, boy, you guys wanted to make sure we knew where it was and what it looks like. You must think that, we wouldn't know otherwise. But yeah, we always want to make sure that that's very recognizable. And we gave them the keys to the car, too. Which, yeah, you got to have the keys to operate it. So that's what it looks like, and it's implemented at SLIO. It sits there right now. It is not actually operating on the grid. It's in what we would call a standalone mode. So it's taking data, and it's computing what it would do if it were connected to the grid. So we can always get this data and look at it and analyze, well, what would it have done to the grid? And so that gives us a good analysis when events happen. So we'll get a phone call from Dimitri or from someone at BPA who says, something really interesting just happened last week. We want to see what your controller would have done if it were connected. And so we'll get this data, and then we'll analyze it, and we'll take a look at it. We'll show it to them. We'll give them a report on it. And that's the kind of thing that they want to see, even when it's not connected. We also have another copy of this, almost pretty much identical, that sits in our lab at Sandia. Now, it's not connected to the grid, but we have that to do all our development work, because they told us, you can't live up here. And Celilo is a fairly high security place. It's a place of, it would be a high value target, let's just put it that way. So they want, you have to be escorted, and so it'd be a real pain to have to be up there for weeks at a time to implement software. So we do all our development in Albuquerque, and then we go up there and we load in the latest software, any changes that we made, and and sometimes we swap out hardware as well. Makes for interesting luggage on an airplane, but yeah, they wonder, ooh, what's that? But we do that periodically so that the thing doesn't get stale with old hardware. So we finally got permission to do testing, and that is not an easy thing. You have to show you've done a lot of simulation studies. PSLF is the one that they prefer to see it in. The Western Electricity Coordinating Council has these baseline models of the grid. And the Western interconnection, just to give you an idea, it's about 18,000, 20,000 buses, 4,000, 5,000 generators, 6,000 transmission lines, just transmission. That's a big system to simulate, and PSLF can handle that. It can actually go up to 80,000. And we did a lot of studies on that, published the studies. BPA looked those over, and then their operations folks got involved. So we kind of migrated through the BPA hierarchy of planning, operations, and cyber, and all the different areas to at each stage as the project moved along. And so when we got to the point where we're ready to do a test, we had to put together a document that showed exactly minute by minute what we wanted to do, and we simulated what it should do based on what we were going to have the controller do, because they wanted to be able to look at that and say, okay, this looks pretty safe. And then they have to get a series of permission signatures. We also have to coordinate with the Los Angeles end. They need to know that we're going to be doing some things. And otherwise, they're like, hey, what are you guys doing up there? So they need to know that. And so this is a plot of the power flow through the AC part. Now, we're not modulating AC power flow. We're modulating DC power flow on that Pacific DC intertie. But if you want to see what's happening with the oscillations, this is the best place to look at it. Look at the COI power flow. COI stands for California-Oregon Interconnection, or intertie. And that's the series of AC lines that goes from BPA down through California. And what this shows is to really, let's put it this way. When they gave us permission to do the test, they said, you're not going to do your first test on the hottest day of the year. And you're not going to do it, if you guys are sitting there and suddenly a line goes down somewhere before you start your test, well, you guys may have to come back or postpone the test to a different time because that day is out. That would definitely disqualify us. So the grid's pretty well behaved, and if the grid's pretty well behaved and you implement your control and you improve damping, you can show mathematically that you improve damping, but a lot of people would look at the plots and they'd say, no big deal. You guys didn't do much of anything. So we needed a way to disturb the grid. Think of it as an impulse response, a hammer to the grid. So there's this thing called the Chief Joseph brake. And I don't know how many of you are familiar with braking resistors. This is the largest in the world, and it's really a one-of-a-kind device. And it is a large resistor that can take up to 1,400 megawatts and dissipate it to ground in about half a second. And it was built in the mid-1970s. You might ask, well, why would they build it? The answer is they needed a remedial action scheme for if the Pacific DC intertie, which is one line, if that goes down and you're pumping 2,500, 3,000 megawatts through it, where does all that power go? Well, the generators, they have to trip off, but generators don't trip off that fast. In other words, they need something that'll buy them time, half a second. 1,400 megawatts, don't have to have all of it. So that's why they built it. So it's a, in case, the worst case happened to the PDCI with no notice, they have a contingency for that. Well, it turns out over the years, and especially since 1996, that it's actually a great way to do testing of the behavior of oscillations on the Western grid, because it shakes up the grid enough that you can really start to see these oscillations, and it excites a lot of different modes, north-south, but a couple others. And so people like Dan Trudnowski have been doing studies using what's called probing data from the PDCI, and a lot of the events that you can't have events that are accidental or trying to do something that could be potentially damaging. Chief Joseph brake is great for that. Half a second, 1,400 megawatts sucked in by that resistor, and then things go back to normal. So it turns out to be a really good way to do testing. And so this is where the Chief Joseph brake is tripped on. It goes for half a second. And the red and black, the red is with no control. The black is with our controller operating in the loop with the grid. And the Chief Joseph brake gets oscillations going. Things are pretty ambient up to that point. Here you see some significant excursions. The amplitude of the peaks and the settling time is improved significantly. Mathematically, the improvement is damping is improved from 11.5%, so higher percent is better, to 16%, which is like a 40% improvement in the damping ratio. So that's a really big improvement. And yet 11.5%, from a practical standpoint, that's pretty good. You're already, but like I said, they weren't going to let us test on a day where this number was much lower than that. We did some other tests as well. So we did some square wave testing, but the net result was the controller consistently improved damping by about this amount, and none of the other modes, and a lot of this was done with forensic after the event analysis, none of the other modes were excited at all as far as having a sort of a peripheral damage. So the do no harm part worked. We've gone back several times since, and we've redone those tests in addition to doing new tests, and the gain in improvement is very consistent. And we've tested this consistently 2017 and again in 2018, and the results are very consistent, confirming that it is improving damping a significant amount, and it also is a dependable kind of improvement. And so we've done, these plots here are the frequency difference. So this is like the input signal to the controller between a couple of the PMUs. And so this is really telling you, how much improvement are you getting in the oscillations. Most people prefer to look at the Coy power flow, which is why I showed that first, but this is kind of something that you really want to see to really drive it home that it's doing what it should be doing. You may notice this thing here, that was unrelated, caused some heartburn. When the operator's looking at it, it's like, did we just do that? And said, no, we didn't do that. That's not us. It was somewhere in the south, unrelated, just happened to happen. I could say more about it, but I won't. Anyway, so the other thing we want to do is to figure out, well, what's our best gain? Now, we don't have an adaptive gain, so we don't tune the gain online. That's something Dimitri has asked us to consider, and we'll probably use some kind of gain scheduling. But we needed to figure out offline, well, what kind of gain, we don't want it to be too high. If it's too high, then we're pushing the DC part too hard. And that's when you start getting this green curve, this ringing effect. And that was with a real high gain. We don't want that. But if the gain is too low, then you're not doing much. So we need to find the sweet spot, which we did through a number of these tests. And the answer seemed to be between 9 and 15 megawatts per millihertz. And the reason we needed to do this is that finally, in May and June of last year, we kept asking them. We said, what we really need to do is what we call a walkaway test, where we're not there for 6 hours, and then we pack up, go home, and disconnect it from the grid. But it'll run for a month at a time without us there. And it took 2 years of testing before they finally gave us permission to do that. And that we had a 4-week test, and that's why we need to know what the gain is, because we're going to set that gain and leave it there. We don't want it too high, we don't want it too low. And so that was the purpose of this testing, was to figure out, okay, what's the best gain for the walkaway test. The walkaway test makes them nervous. So they had our cell phone numbers right by the operator desk, and we were like making sure that we could be contacted anytime, 24/7, and immediately respond if there was an issue. Fortunately, there was not. We did some other tests. I won't say too much about this on forced oscillations. I don't know if you know much about forced oscillations. These are oscillations that are induced on the grid. They're not a natural part of the grid. They happen because of some event, not necessarily a dramatic event. It could be like a valve issue at a hydro plant. And the frequency of these force oscillations can be anywhere in the 0.1 to 10 hertz or so. So it covers a wide range. We don't do anything in our controller for the higher frequency oscillations, but at least we wanted to show that we can improve a 0.4 hertz forced oscillation. So we asked them for permission to do a forced oscillation on the grid, and they said, "What? You kidding?" And so no, we didn't get permission to do a forced oscillation. The one we wanted to do was from Grand Coulee Dam, and that meant getting permission from Bureau of Reclamation, and that was just too much to coordinate, so we didn't get it. So we did something locally with what's called the probing signal generator. And offline, I can talk to you, and so can my boss, who's telling me, okay, yeah, it doesn't really tell you. The bottom line is we would need to do more to show that the controller does improve damping significantly to force oscillations than this. But it does seem to improve disturbance rejection, as you can see between the blue, which is with control, and the red without. So during this 4-week test, there were several things that happened on the grid. And most of these events were on the DC side. So stuff happens on the DC side too. And sometimes it might be like a trip, like here, where the DC line goes down very briefly and comes back up. In this case, that's 1,800, 1,900 megawatts. That's a pretty significant amount in a course of tenth of a second or so. And if you have a before and after, which is kind of hard to get, well, it turned out we do. May 6th, which was before our walkaway test, June 11th, which was during, we can actually show how the controller behaved. And the controller, what it did on May 6th, what it did on May 6th, which was when the controller was not connected, and then what it did on June 11th, seems to be a little bit of improvement here in terms of convergence back. Now, zero, I should point out, if you're looking at that, saying, wait, what's zero? Zero is just subtracting the delta off of the PDCI power flow, the scheduled power flow, changes about once an hour. So, over a course of a few seconds, it doesn't change unless there's a trip. And so zero meant it's at its regular value. We just zero referenced the plot. And so it shows that the controller really did a good job on reducing the hiccups as a result of the PDCI trip. And it wasn't intended to do that. We didn't build it or design it to fix a DC event. That's a different issue. But the fact that not only did it not make it worse, but kind of improves it a little bit was encouraging to the operators there. And so the damping controller, as I said, performed as it should. We wanted to make sure it didn't get confused or anything, so no problem there. That's all this plot is showing you. So we felt pretty good about what the controller was doing for the test that we were able to perform. So now I want to shift gears a little bit and talk to you about the delays associated with putting a PMU in a feedback loop. There are several different kinds of delays, and so this time sequence is to sort of tell you what the difference is between these different delays. The PMU delay is really a function of the manufacturer of the PMU. How wide is the window over which they take data to get the measurement that they're sending out? And of course, that's a moving window. And typically, it's 40 to 50 milliseconds. It depends on the manufacturer. Some cases, you can change settings. The communication delay is the one we care about the most. That's a delay from when the PMU sends information to when the controller gets it. And that was very low, 16 millisecond mean, and it didn't range very much. It only went up to 40 milliseconds, which is excellent. I say it has a heavy tail, so it's like a normal distribution. Since the mean is 16 and the low is 15, obviously 40 is a heavier tail. But 40 milliseconds is a very low delay compared to a oscillation of 0.4 hertz, 2.5 seconds. If you, just for instance, if you had a say a 500 millisecond delay. 500 milliseconds, that's 20%. That's 20% of the entire period. That's 40% of the half cycle. You're almost out of phase injecting your control signal. You can actually make it worse. And that's something, delay gets you what's called a non-minimum phase system, right half plane zero. And if you push a system with a right half plane zero with high enough gain, you can drive it unstable. In other words, you drive a left-hand pole over to the right-hand side. Of course, we don't want that. The control processing delay, this thing ran at 60 hertz update cycle for the controller. That's the rate at which PMU data is coming. And the worst case is 17, because that's 16 point whatever milliseconds. So roughly 17 milliseconds. The normal is around 11. Command delay is the amount of delay that from when the PDCI gets the command to when it is physically injected into the grid. And that is roughly 10, 15 milliseconds. So the total delay, what we call round-trip delay, was anywhere from as low as 69 to as high as 113. And that's excellent because our tolerance was 150 milliseconds, which is conservative. We could probably go to 200. We got very good performance with those delay numbers. We felt very good about it. And the data quality was excellent. BPA's network is a sterling network. Not every utility can afford that kind of a network, but just to give you some idea, that was one of the best networks in terms of data quality, consistency, and low latencies. That's not the only thing that can go wrong, though, using PMU data in a feedback loop. You can have inconsistent delays between the packets. In other words, it's supposed to be every 60 milliseconds PMU turns out data. So every 16 milliseconds you get another data packet. It's not quite that good. It can vary some. And that was a little bit of a surprise to us. We were thinking it would be pretty consistent, but it's not, which means you might get 2 packets in one update cycle and 0 in another. And so that can affect the frequency estimation when you don't have, because we're determining the frequency from the phase angle, when you don't have consistent data arrival. So that was something that we needed to address. And so what we concluded is that the do no harm commandment takes priority over everything. And that told us that without any question, we need time alignment. The packets in the north that we use in the feedback signal and the packets in the south, they have to match within a very, very small range. They cannot be from, one is from 16 milliseconds before the other. Even that small of a range, we said we need the delay to be consistent. We have to have and enforce time alignment. And so that was critical to the controller. And so that's what this means here. North and south have to have the same PMU timestamp. And the supervisory system makes sure that everything is time aligned. And if the data is too far apart in time, then the controller is disarmed. Now, we have more than one PMU. As I said, we have 16 PMU pairs. So that gives us some margin of error. We can switch to a different one. There were other issues where the data just doesn't come in. Again, the redundancy, diversity helps. And there were, this almost never happened on BPA system. Other utilities have reported that this happens more often, where there's no timestamps, or you get the same value 2 cycles or multiple cycles in a row. So we have a flag for that that says, no, this is too close together. That can't happen. That's a definite glitch. So again, that helps determine do we switch PMU pairs. So I'm almost done here. That is the PDCI damping controller, which we implemented in hardware. I mentioned way back at the beginning of the talk that we got co-funding by Emre from the energy storage program. You may ask, well, you didn't use energy storage here. Why would he fund this? Well, because going forward on the grid, energy storage, which now, batteries, utility scale batteries, you won't find much of that on the grid right now. The belief is, and the expectation is, that costs will come down, the value proposition out of energy storage will become more obvious, and so the case can be made that people will start putting energy storage at different locations on the grid. So this is sort of a fake Western grid here, where the diamonds are the energy storage sites that don't now exist. So we did this in simulation. And what we wanted to do was to figure out, well, how much improvement in damping can we get if we have one energy storage site? How big does it need to be, and where does it need to be to damp the north-south mode? We did a study on that. You need 50 to 100 megawatts, and it needed to be pretty co-located either in the north or the south. Then we said, well, we got the PDCI there. Why not put it so that it can do some good for the east-west mode? And the answer came back, stick it in Wyoming, 50 megawatt storage. Well, who's going to put 50 megawatts of storage in Wyoming that is only going to be used a few seconds at a time, maybe really only necessary once a week, once a month? That's a huge investment. So after that study, we changed gears and said, okay, what if you have lots of energy storage sites that aren't very big and they're there for another purpose? They're already being used for something else. And since our signal is energy neutral, we're not sucking the state of charge up or down. That allows us to perhaps harness the energy storage very briefly to inject real power into the grid at a lot of different places that could be used for damping. And none of these sites need to be that big. They could be maybe a megawatt of storage. And with a bunch of these engaged, you can actually improve damping. You need to coordinate it. We didn't quite get to the algorithm for coordination on a grid scale level, but that is something that is still, we're still going to investigate that going forward. And this is just a quick example that we did this was in MATLAB. And this is a pole plot that shows all the different modes or different poles, zeros or different poles in this case. This is the east-west mode, and you can see the damping improved quite a bit from having these sites. This is a sort of a static heat map. I was really impressed with the display you guys have. I guess that's on this floor, or yeah, it's on this floor. And that had that real-time heat map that showed the frequency variations. That was pretty cool. This is a static map, but it can be done on MATLAB. And we actually distributed this to a bunch of Western utilities. And it shows red, blue, oscillating against each other, 180 degrees out of phase. The size of these circles is proportional to the participation of that site in that mode. And the sticks coming out of it are the phase angle. And this is the last slide. Well, I have a couple conclusions, but I can wrap up here. We also wanted to do a proof of feasibility study. And Sandia has a wind facility in Lubbock, Texas. And we wanted to see, well, how about modulating the torque for the wind turbine? And could we do that and possibly improve the oscillations on the grid? And the only issue here is that Lubbock, Texas is not in the western grid. It's actually in the eastern grid. It's not in ERCOT, although it probably will be in a few years. And we took some PMUs from different locations. And for this experiment, we didn't have the great fiber optic network BPA has. We used public IP. And we did that on purpose because we wanted to see, okay, let's use not bad, but let's just use a normal network that's not that good. Is this pie in the sky? Well, it turns out, in terms of the delays, it's more, and there are some more data issues, but you can still do real-time control to modulate the torque from Albuquerque to Lubbock, getting PMU measurements from other places not co-located with either one. So it's proof of feasibility because, well, Albuquerque's in the western grid, Lubbock is in the east, so you're not actually controlling a real mode. Just wanted to make that clear. So that was a small, quick feasibility study, and it's very encouraging that this can be done with wind. So overall with the project, it's the first time in North America that PMUs have been used for real-time feedback control. We've designed the controller so that it isn't just a one-trick pony, only works on PDCI, can't use it on wind or energy storage. Indeed, you can. We made no hardware changes for the wind case, so we were able to use it as is. We have a do no harm supervisory system, which we have to have, and that's a good lesson for everybody if you're ever working on a really critical controller in the field, that you got to have something like that. We did a whole lot of background work before we're ever allowed to test, so we have lots and lots of what I call eigensystem analysis tools and visualization tools. I just showed you one, and models for like a two-area model that you might just do in MATLAB. We have one that's used the Power System Toolbox that is a third-party toolbox for MATLAB, and PSLF. And these are, they go from just a couple buses on up to 18,000. We won an R&D 100 award for this project in 2017. If you haven't heard of R&D 100, well, Elu has won 2 of them, I believe. And she just won one just this past time. We won one the year before. We've published, this number has grown already, so we're in the 20s now on publications, more journal papers. We did file a patent a year ago. It's still pending, and we have been pursuing commercialization of this. BPA said, this is great, but we want to buy it from a vendor. We don't want to buy it. We don't want to have to call Dave at Sandia and say, it's not working right. You come out here and fix it. They want a vendor, with an 800 number and 24/7 service, and we don't do that at Sandia. So I should say we don't. Actually, in a few rare cases, one-of-a-kind things, we do. But BPA said, can you find a vendor for us that will do this? And so we're looking, and we've talked to several vendors and applied for a DOE fund to move it from, it's been proven, we got something that works, we've tested on the real grid, now we need a vendor so that you can just pick up the phone and order it, or go on the web and order it. And that's the next stage of that project. Yeah, that's pretty much what I've already mentioned. They have a couple companies to talk to, Schweitzer, ABB, and the future research, we're doing transient stability. That's the big thing that we're working on now. And the damping controller works for that too, but you need a little bit more power, so we might consider a different actuator. And as I mentioned, we're looking at decentralized control, and there's data issues. We're looking at machine learning. A lot of the things you guys are doing. So I think, and by the way, I don't know if it was mentioned here, but Sandia just joined CURENT. We were shamed into it because the other labs, PNNL, NREL, Lawrence Livermore, all belong, well, and of course Oak Ridge, all belong. And so they're like, well, what's up with you? You guys need to belong. And for those of you who don't know, I used to work at Oak Ridge. It's been, I've worked there for 7 years. It's been 20 years since I left to go to Sandia. But I was an adjunct professor here at UT, and I actually taught a class. And I worked a lot with, you probably don't, I know he's retired, Doug Birdwell, Professor Birdwell. So I just thought I'd throw that in. So I lived in Knoxville for 7 years. So I know all about the rain you guys get. It's happened before. So I'll take any questions you guys have.
I'm sorry. We're short of time. I know some of the students have to leave, so if you guys need to get up and leave, that's fine. You have other classes. Otherwise, we can take a few questions.
Sure. Be happy to answer questions.
Students, if you leave, make sure you sign. When you leave, sign the sign-up sheets outside.
Yes.
Thank you for the presentation. It's very impressive.
Welcome.
I have a few questions. What you have presented today, I think is mature enough to be operating in the real system, in the closed loop environment. But now it's in the standalone, open loop environment. So what's the barrier, or what would be the barrier for the last step?
Well, a couple things. It has to get approval from WEC, which is the Coordinating Council for the Western Grid. And so there's what's called NERC SIP compliance. And since we're using PMUs in a real-time feedback loop, there's cybersecurity issues associated with that.
Mm-hmm.
We've addressed some of those, some we haven't, and the funding to do that isn't there right now because that would have to be part of a operational decision made by BPA going forward. And at the moment, they have not made that decision yet.
Mm-hmm.
So that's the number one, is NERC-CIP compliance. And the other issue is a little bit of hardware. I guess you call it hardening of the hardware.
Mm-hmm.
To be a little bit, I mean, it works fine. It's in the environment. It works just fine. But there's things like going fanless with the processors. Right now we have a fan in there. Well, actually, we had the worst one. That gets off topic a little bit, but we had a router that had 8 fans in it that BPA gave us, and made so much noise it was a hearing hazard.
Okay.
They moved that, but that wasn't on us. We didn't contribute to that. With the door closed in that refrigerator, it's very quiet.
Okay.
No louder than the ambient noise in the room it's in.
Okay, thank you. Another question is, I noticed that the control gain of the controller is a constant value. So do you think it's necessary and feasible to tune the control gain in the online environment to make it adaptive?
It depends on the limits that were given. For the walkaway test, they actually lowered it from plus minus 125 to plus minus 25. In other words, they put training wheels on us, big training wheels, because it's a 4-week test and we're not there. So they said, well, we'd feel better with a smaller authority. I think that what we have gotten from that is the gain with the higher limits. You might want to schedule a gain to be lower under more ambient circumstances, and maybe a little higher in other circumstances, so that you wouldn't. I don't think we would have like a continuously adaptive type of control gain structure, though that's a possibility. But that introduces yet another layer of dynamics, nonlinear dynamics, to your system, and that would definitely delay any deployment. So it would be more of a gain scheduling type of algorithm if we did that. Yep.
Congratulations on this work, and I'm very glad to see this happen in the U.S., not just other countries of the world, because the idea is pretty mature idea. And I noticed actually you use 2 PMUs, even you call one north, one south, actually both located in Oregon, right? So those are now the best ideal locations to play those sensors. And yeah, but my point is, yeah, understand that once, because this project is BPA project.
Well,
we want to measure data from the same territory, also do the control locally. But Mike, yeah.
I was going to say, I'm impressed. I'm glad you noticed that. Hoping nobody would.
Yeah, I'm fine with that. Yeah, I fully understand the engineering difficulty, because I really appreciate this work to make it happen. But my only single concern is with the communication tolerance you mentioned. Okay. And you gave an example, you're saying even because right now the delay is about within 100 milliseconds, so which is fine, pretty good. Yep. And you show one example, if it's 500 milliseconds, you comment that should be okay, because that's still about a fifth, so maybe a fourth of the half period, right? Because remember, right now you're now using the ideal controller, right? You take the data from the one side of the oscillation, so which means the difference between those 2 PMU are not that huge. It's not like a half period. Right. So 500 milliseconds, I doubt that will. I guess that may cause some problems with the controller.
First of all, that was a very good observation you made, and right at the beginning of the project, we told BPA, okay, we need PMUs in the north, and we need them in the south, and we need something near LA. And immediately they said no. And we said, well, to really make this work, that's what we need. And they just said no. And they repeated, and it became hell no. And the reason is there's technical issues associated with trying to use real-time data from that far away. Number one is the fact that they don't own it. They don't control it. So from a cyber standpoint, their cyber people said, if it's coming from outside our system and we're trying to make decisions based on it in real time, no way. We will not allow that. So we did not get permission to use that data or to use PMUs. So where they say necessity is the mother of invention, we spent a lot of the project looking at, well, can we find another PMU in BPA system that can serve as a proxy for what is happening in Southern California? And we did a lot of studies, and because, I mean, literally we had sleepless nights over this, because what we have really is what you would call a non-collocated sensor actuator pair. Actuator in LA, sensor, you know, in Oregon, California border. So what we did is we did a ton of simulation studies, and every single example we found is that it did correlate to what was coming out of Southern California. So we did lots of simulations using the PMU in the north, the same one we're using now, and the one in LA. And we did those simulations and compared them to the one, the north to the one that we're actually using. And we got remarkably close data. But I agree, there is a concern here because you've got a lot of dynamics between the Oregon border and Los Angeles in the system. And so, you know, you might ask the logical question as a control theory guy, say, well, isn't it possible you got some dynamics there? Non-collocated sensor actuator, you know, because I did a lot of work, my PhD work in flexible structures. And if you put a sensor and an actuator, like a shaker to damp oscillations in a flexible truss, but if they're not at the same place, you can actually inadvertently excite modes. It's called spillover, that you're not directly controlling. And so the question is, yeah, if you have a PMU that isn't right where the ideal spot, is it possible that you could excite other modes? Well, that's where the supervisor comes in. And right now, the response to that is we would just disarm the controller, do no harm. But so far, we haven't found that case in simulations or in any testing. But it is a concern, without any question.
We have a question from the audience, from the web audience, and then we'll go one more. The question is, what is the increase of megawatt transfer capability of COI by using the dampening controller?
That's an excellent question, and it's one that we had to consider for the R&D 100 application. That's kind of a bottom line kind of thing that, you know, the layman would say, well, you know, how much? And the improvement in terms of in terms of megawatts, it was in the several hundred megawatt case. So it's maybe 10% of the COI, because I think that's a 4,000 megawatt limited corridor. And I think, I mean, these are total ballpark numbers that are not, and they could vary a lot, but it was up to like 500 megawatts potentially, which is a lot of revenue. Yep.
Hi. My question is, in the future with changing inertias in WEC and a lot of other changes, I think I read somewhere they're even planning to upgrade PDCI to maybe even 3,800 megawatts. How does this controller adapt to like a future scenario with a completely different?
That's another really good question. And well, Ray Byrne headed a study a few years ago where we looked at the high penetration scenarios of the future in the WEC. PV and wind going, what, 50%, I think over 50% scenario, or up to 50% scenarios. And the general conclusion was that the damping of most of the modes degrades slightly, but not that much. But in terms of our damping controller, as I said, it's somewhat actuator agnostic, and under 1 hertz oscillations, the way it's positioned now in the PDCI, it's only going to improve the north-south, but in terms of how it would operate, as long as the PDCI is there, it should still be able to improve those modes by a comparable amount. But at that point, that's why we started looking at wind, and I know Hector is looking at PV, and we also looked at energy storage, because that is the future grid. Inverter connected resources, and we are looking at that, and I know you guys are too. That is the future grid, the loss of inertia, and damping controller I think plays an even bigger role in that case. because it's more logically implemented on a power electronic situation.
So we will have today's seminar, the slides and the actual recorded seminar out on our website for those of you on the web and others that might want to share that later. Please join me in thanking our presenter today.
Thank you. Thank you. All right, thank you very much. Really enjoyed delivering the talk. I'm glad you guys came out and asked great questions.